All right. So in this video, we are going to discuss the wave packet or wave group that's associated with the material particle. We have already seen that if we assume that there is a de Broglie wave associated with a microscopic particle, then the velocity of this wave comes out to be greater than that of speed of light. So this means that the assumption of having a single wave train associated with a material particle is not right. It doesn't work in the situation, because if we extend this idea, then the wave that we are assuming is associated with the particle will be far ahead of material particle, and at the same time it's a violation of the postulates of special theory of relativity. So in this case now, Schrödinger used the idea of a wave packet. So what Schrödinger postulated is that a material particle is associated with a group of waves, and if it is associated with a group of waves, the waves that are making the group have slightly different velocities, they have slightly different wavelengths, they have slightly different frequencies. So if these waves interfere constructively, which probably happens in vicinity of the material particle, then the constructive interference takes place, and the probability of finding the particle becomes maximum. The particle has a probability to be localized in that domain. But at the same time, if we go away from this particle, the waves that interfere, who have different frequencies, they interfere destructively, so that the amplitude of the resultant wave that comes out sharply boils down to zero. So the constructive interference of these waves leads to a wave group, and what is proposed by the Schrödinger is that there is a maximum probability of localizing the particle in that zone, and the probability goes zero as we move away from the group where the constructive interference has taken place. So the point is here that you can see that this is the amplitude of a wave packet. You see that this is the region where the constructive interference of a long range of waves has taken place, and probably within these amplitudes there is a probability of localizing the particle, and outside this region, so this is a region of constructive interference of these waves, and anything outside this region is attributed to the destructive interference of the waves. So this group of waves that has a collective velocity, this collective velocity of this group of waves is called as group velocity. Now, for the sake of argument, if we take two wave trains. If we take two wave trains having the displacement as a, say, cos omega t minus kx, and choose another having same amplitude cos omega plus d omega, t minus k plus dk x. Now, if we take a situation in which there is a set of two wave trains, and these two wave trains are superimposing on each other, and you can really see here that you have the two waves having displacements as y1 and y2 with respect to their mean positions, and their amplitudes are same, but there is a slight variation in their angular frequency, and there is a slight variation in their propagation vector. As all of you know, this omega represents the angular frequency, and this k is called as propagation vector. So we can have a simple mathematical treatment, and we can solve these two equations. And the point of solving these two equations is that we will be applying superposition principle. When we use the superposition principle, which probably will be y is y1 plus y2, we go with certain mathematical manipulations, we go with certain mathematical approximations. In doing so, we come up with the result of mathematical interpretation of group velocity, that's Vg, and that comes out to be equal to delta omega divided by delta k. So this Vg comes as a result of superimposing these two waves, these two wave trains, superimposing them mathematically and simplifying these equations using certain manipulations, using certain approximations. We come across the result as the group velocity. This group velocity comes out to be equal to delta omega divided by delta k. Now delta omega is a small change in angular frequency, and delta k is the small change in propagation vector. If we further boil down this equation, we come up with the result. That this Vg, which is the velocity of this wave packet, velocity of this group of waves, it comes out to be equal to the velocity of the material particle. Velocity of material particle. So what does it mean? It means that the group velocity, the collective velocity of the waves, which is in vicinity of the material particle, this velocity is coming out to be nearly equal to the velocity of a particle, signifying the fact that this particle is in vicinity of the wave packet. So this way we have seen that the idea of